Following on from the previous video, we're going to look at how we can recover some of the heat from the exhaust gases in order to improve the efficiency of our process. So the question on the screen here, which is an extension to the previous question, says the exhaust gases from the gas turbine described previously pass through a heat recovery steam generator, HRSG, which provides sufficient energy to power the compressor in the gas turbine. So we're recovering that heat, we're passing it through a steam generator, and the power output that's produced is sufficient to power our compressor in the system. As a result, the net power output from the gas turbine plant is equal to the power output from the turbine itself. So here, our gas turbine isn't powering the compressor. The compressor is being powered using the heat energy that's been recovered from the combusted fuel. It goes on to say that all other conditions and parameters remain constant for the gas turbine. We're asked to calculate the temperature of the air exiting the compressor, the power required to run the compressor, the net power output from the turbine, and the new efficiency of the cycle. So we're asked to calculate T2, which we already have. That's the temperature of air exiting the compressor. We're asked to calculate the power required to run the compressor. Well, the power required to run the compressor is going to be P in. We're then asked to calculate the net power output from the turbine. Well, what we're being told here is that P in is being provided by the heat recovered from the exhaust gases. So this time, P net is just going to equal P out. And we're asked to determine that. And finally, we're asked for the new efficiency of the cycle. Okay, so before we do any more calculations, we can see that we have T2 in Kelvin, and at the bottom we have T4 in Kelvin. But what I'm going to do is I'm going to convert T1 into Kelvin. T1 is 15 degrees C, and if we add 273.15 to that, we get 288.15. So we have T1. The other temperature I'm going to convert to Kelvin then is T3, and then all of our temperatures will be in Kelvin. So 880 plus 273.15 equals 1153.15. So since none of our temperatures T1, T2, T3 or T4 are changing, we now have all of the temperatures we need for this cycle. Okay, so the first thing that we're asked to calculate here is P in. Now, the calculation for P in is as follows. P in equals m dot, specific heat capacity at constant pressure, the temperature at the exit of the compressor minus the temperature at the entry of the compressor. Therefore, P in is 1.6 times 1005. We have T2 in Kelvin, 552.32. And we have T1 in Kelvin, 288.15. Now, running those through the calculator gives us the power in, or the power consumed by the compressor, equal to 424,785. So converting that into kilowatts, we have 424.79 kilowatts. So in the previous example, we were providing 424.8 kilowatts of energy to our compressor, and that was being drawn directly from our turbine. So we calculated our net power, 462.10 kilowatts, but 424.79 kilowatts was being lost because it was being used to power our compressor. Well, in this new scenario then, this 424.79 is being provided by the exhaust heat gases, so all of the power output is coming from the turbine. Now there's a couple of ways we can determine this. We can add the power input to our original net power output, and that would give us the original power output. And I'll demonstrate this now. So in the previous example, we had our net power output of 426.10 kilowatts, and the power that was required to run the compressor was our 424.79 kilowatts. Now in this instance, all of the power output from our turbine is going to be used to power our electrical generator or similar. So what we can do is we can add the original net power, P net, and the power required to power our compressor in order to get the power output from our turbine. So the power output from our turbine in this case then is the original net power output, 462.10, plus the power that was being consumed by the compressor, 424.79, which gives us a power output this time of 886.89. And that's our useful power output. All of that is being transferred to our generator. So this time then, our efficiency is our useful power output from the gas turbine plant, and this time it is 886.89 divided by the heat input. Now the heat input to the process is exactly the same as before because the additional heat provided here in order to power the compressor comes from the hot exhaust gases. So our heat input remains as 966.13, giving us an overall cycle efficiency this time equal to 91.80%. So we can see this time our efficiency is significantly higher than our gas turbine operating on the simple cycle. Now, as mentioned, there is a second way that we can calculate this efficiency, and we can check the values that we've just obtained there. So let's make a note of our efficiency of 91.80, and then we'll look at an alternative method of calculating this in order to compare the results that we've obtained. Okay, so the other way that we can determine our power output is using our standard equation, mass flow rate, times specific heat capacity, times the temperature at the outlet of the turbine, well, the outlet is T4, minus the temperature at the inlet, T3. Now we have all of these values in SI units and in Kelvin, so our mass flow rate then is 1.6, our specific heat capacity at constant pressure is 1005, T4 is 601.61, and T3 is 1153.15. So running that through the calculator gives us a P out value equal to minus, because the energy is leaving the process, 886.88 kilowatts. Now we're interested in the magnitude of P out, and the magnitude of P out is just 886.88. Now once again we can calculate our efficiency. Because we're powering our compressor here, P in, using the exhaust gases, we've stated that P net equals P out. So our efficiency is P net over phi in. P net is the same as P out, so we have 886.88, and phi in is 966.13, giving us our efficiency of 91.80%. Now, it is worth mentioning that this efficiency is very high, and in fact it's significantly higher than we would actually obtain from this type of cycle. And the reason for that is the assumptions that we've made. We assumed that our compression and our expansion were isentropic, but in actual fact that wouldn't necessarily be the case. We've also assumed that the heating in the combustion chamber takes place at constant pressure. And the final assumption that we've made is that the exhaust gases are fed back into our compressor. And again, that wouldn't be the case. Further assumptions here are that we've managed to recover the heat in the exhaust gases, and the energy contained within that exhaust gas has been sufficient to fully power our compressor. So once again, we've made a number of assumptions, but the key point to note is that our efficiency, using the combined cycle here, is significantly higher than the efficiency of our simple cycle. Let's take a look at one more example, and this time we're going to be using regenerative heating, where the exhaust gases are used to preheat the air entering the combustion chamber. So in this example, it states that the exhaust gases from the gas turbine described previously are used to preheat the air entering the combustion chamber. So this is what's known as regenerative heating. So there it states through heat regeneration. As a result, the temperature of the air-fuel mixture exiting the combustion chamber is increased by 65 degrees. Well, the exit of the combustion chamber is position 3. So T3 is going to be increased by 65 degrees. Previously, it was 880 degrees. 880 plus 65 is 945. So let's remove our old T3 value. And instead of 880, we're going to have 945. Note that that's degrees Celsius. If we want to convert that to Kelvin, we need to add 273.15. And 945 plus 273.15 is 1218.15. 1218.15 Kelvin. We're asked to calculate the power output from the turbine once again, so P out. The new net power, P net. Now note this time the turbine is providing the work to the compressor, so we need to factor that in. And the new efficiency of the plant. So P out, P net and the efficiency. So let's begin by calculating our new P out value. P out, as we said previously, is the mass flow rate times the specific heat capacity at constant pressure. The temperature at the exit of the turbine is T4, and the entrance is T3. So the first important thing to note here is that we have a value for T3, but we don't yet have a value for T4. Now the reason the value for T4 is going to change is because we have an isentropic process or an isentropic expansion in the turbine. Therefore, if we increase T3 and our pressure at position 3 and position 4 remains the same, then we know our temperature at position 4 is going to change. We previously had a value of T4 equal to 601.61 down in the bottom left hand corner, but we need to recalculate that value before we can calculate our new power output. So the equation that we use for this is as follows. T4 equals T3 multiplied by P4 over P3 to the power of 1 minus 1 over gamma. Now that's a formula that we have seen previously. So inputting some values then, we know our new value of T3 is 1218.15. We know P4 is the same as P1, 1 bar, and we know that P3 is the same as P2, or 9.75 bar. We have our value for gamma, so we have 1 minus 1 over 1.4, giving us our new value of T4 equal to 635.518, or 635.52 to 2 decimal places. So let's cross out the previous value of T4, and our new value then is 635.52 Kelvin. So continuing with our calculation then, we can now determine the P out, or the power output from the turbine. And the power output from the turbine this time is our mass flow rate, which remains as 1.6, times the specific heat capacity, 1005, times T4, well we've just calculated T4, 635.52, minus T3, and this is our new T3 value, of 1218.15, and running that through the calculator then gives us a P out value equal to minus 936,869, but we're working in kilowatts, so we get minus 936.87, accurate to 2 decimal places. Now the reason this is negative is because energy is leaving the process. The combusted air-fuel mixture are doing work to turn the turbine. What we're actually interested in is the magnitude of P out, and if we're using the magnitude of P out, then we can lose our minus there. So the power output from the turbine is 936.87 kilowatts. Let's make a note at the top. We have P out equals 936.87. Our units there are kilowatts. So next then, we need to calculate our net power. So let's clear some space and then we'll look at our calculation for net power. So we've seen this formula previously. We know that P net, the net power output or the useful power output, is the magnitude of P out, which is the output from our turbine, minus P in. Now the reason we're subtracting this P in value is because our turbine and our compressor are on the same shaft. Therefore, any requirements of our compressor are being provided by our turbine before we get that useful energy out. So we said the power output from the turbine was 936.87 kilowatts at the top there, but not all of that power is going to be useful. Some of that is going to be lost in powering our compressor. Now, we calculated the power required to run our compressor previously, and the value we determined for P in was 424.79. Earlier in this video, we talked about how a heat recovery steam generator could potentially power our compressor, but the compressor requirements or the power required by the compressor remains unchanged. So we're going to use the same value of 424.79 kilowatts. Therefore, we have our magnitude of P out is 936.87. The power input to our compressor is 424.79, giving us a net power output or useful power output equal to 512.08 kilowatts. What this shows is the power required to run the compressor is quite significant and it has an impact on our useful power output. So the last calculation that we need to carry out then is for our efficiency. And we know that efficiency is net power output divided by P input. What we're basically saying here is how much of the heat energy input can we convert to useful power output. Now once again, we previously calculated the heat input as 966.13, and the heat input's going to remain unchanged. The reasons behind this is because the mass flow rate of fuel and the rate at which the fuel's being combusted is the same, therefore the rate that energy is being released by that combustible fuel is also staying the same. So let's run our calculation. We have 512.08 for the net power output. We have 966.13 for the rate of heat input, giving us, as a decimal, an efficiency equal to 0.5300 or 53.00%. So just to summarise, we've looked at three different scenarios there. The first scenario was for a simple gas turbine, and we found that we had an efficiency of 47.83%. In our second scenario, we had a heat recovery steam generator providing the power from our compressor and effectively powering our compressor to run the process. In that example, we had a theoretical efficiency of 91.8%. And then finally, we've looked at an example involving heat regeneration, where the air entering the combustion chamber is preheated in order to achieve a higher temperature at the output of the combustion chamber. And when we expand our turbine, we're able to generate greater net power. And in that example, we saw a theoretical efficiency slightly higher than the simple cycle of 53%. Anyway, I hope you found this video useful and thanks for listening.